Hello everyone, my name is Naoto Ohsaka. In this video, I'm going to show you asymptotically optimal inapproximability of the EK-SAT reconfiguration problem. This is a joint work with Shuichi Hirahara. Let us begin with the E3-SAT reconfiguration problem. Suppose that we are given a 3CNF formula phi, which consists of 4 clauses over 4 variables. We are also given a pair of each satisfying assignments denoted by alpha S and alpha E. And the slide shows the Boolean hypercube. The objective of this problem is to decide if there exists a path from alpha S to alpha E on the Boolean hypercube that consists only of satisfying assignments for formula phi. You can see that this input is a yes instance because you can find a path from alpha S to alpha E consisting only of satisfying assignments. How about this input? This input is a no instance. To see why this is a no instance, let us look at the subgraph of the Boolean hypercube induced by all satisfying assignments. Then you can see that alpha S and alpha E belong to different connected components, so they are not reachable. The study of the reconfiguration problems over Boolean formulas was originally motivated by the analysis of the solution space for Boolean formulas. For random instances, it is known that the solution space breaks down into exponentially many clusters in a certain density regime. And such a structure can be used to explain the performance of SAT solvers. On the other hand, in the worst-case scenario, Gopalan, Colaitis, Madeva, and Papadomitriou proved the dichotomy theorem, which classifies the complexity of every reconfiguration problem over Boolean formulas into P or P-space complete. In the P case, the diameter of the connected components of the solution space is linear with respect to the number of variables. In the P-space completeness case, the diameter of the connected components can be exponential. In this study, we will focus on maximum E3-SAT reconfiguration, which is an approximate version of E3-SAT reconfiguration. Suppose that we are given a Boolean formula psi, which consists of 6 clauses over 4 variables. And we are also given a pair of each satisfying assignments, alpha S and alpha E. In this figure, each assignment enclosed by a blue double line satisfies 5 over 6 clauses, and each assignment enclosed by a red dashed line satisfies 4 over 6 clauses. The objective of this problem is to find a path from alpha S to alpha E that maximizes the minimum fraction of satisfied clauses. Consider, for example, a path from alpha S to alpha E shown in the slide. Since this path contains an assignment enclosed by red dashed line, the objective value of this path is equal to 4 divided by 6. But you can find a better path. The path from alpha S to alpha E shown in the slide contains an assignment that satisfies at least 5 clauses over 6. So the objective value of this path is 5 divided by 6. And this is an optimal path. Now let us briefly review the complexity of maximum EK-SAT reconfiguration. It is known that maximum EK-SAT reconfiguration is P-space hard to solve exactly. This is because EK-SAT reconfiguration problem is P-space complete. And it is also NP hard to approximate within a constant factor. Since the exact solution is p-space hard, the NP hardness result seems not optimal. And recently, this problem was shown to be p-space hard to approximate within a constant factor. So the immediate question is, what is the asymptotic behavior of approximability with respect to the closed width k? Our contribution is to demonstrate that the optimal approximation factor is 1 minus order of 1 over k. Specifically, on the algorithmic side, we developed a polynomial time approximation algorithm with approximation factor 1 minus 2.5 over k. On the hardness side, we show that 1 minus 1 over 10 k factor approximation is p-space complete. We also proved that 1 minus 1 over 8 k factor approximation is NP hard. So these results imply the asymptotically optimal approximability of EK-SAT reconfiguration. But you might think, so what? There are similar results for approximability of reconfiguration problems. So I will explain why our results are interesting. The first reason is that our results imply the structure of the solution space for CNF formula. Recall that a random assignment satisfies 1 minus 1 over 2 to the k fraction of clauses in expectation. By using the concentration inequality, we can show that only exponentially small fraction of assignments do not satisfy 1 minus 1 over 10 times k fraction of clauses. In other words, most of the assignments satisfy most of the clauses. Our results imply that deleting exponentially rare bad assignments makes the ST connectivity problem p-space hard. The second reason is that this is the first reconfiguration problem that is harder to approximate compared to its NP analog. The table shows the approximation threshold for some reconfiguration problem and its NP analog. You can see that other than EK-SAT reconfiguration problem, every reconfiguration problem is not harder than its NP analog. So our results mean that a reconfiguration problem could be easier or could be harder than its NP analog in terms of approximability. In the remainder of this talk, I'm going to present a proof overview of the p-space hardness of 1 minus 1 over 1.92 to the k factor approximation. The proof of this hardness result is still non-trivial. Let us first formulate the gap EK-SAT reconfiguration problem. Similar to the max-min EK-SAT reconfiguration, we are given a KCNF formula phi and a pair of each satisfying assignments alpha s and alpha e. Let opt denote the optimal value of max-min EK-SAT reconfiguration. Then the gap EK-SAT reconfiguration requires to distinguish between the completeness case and the soundness case. In the completeness case, the optimal value is equal to 1, which means that there exists a path from alpha s to alpha e such that every assignment satisfies all clauses. In the soundness case, the optimal value is less than 1 minus epsilon, which means that for every possible path from alpha s to alpha e, there exists some assignment that violates at least epsilon fraction of clauses. In the first attempt, we will show the hardness of 1 minus omega 2 to the minus k factor approximation. The proof is based on a gap-preserving reduction from maximum E3 sat reconfiguration to maximum EK sat reconfiguration. Suppose that we are given a formula phi, which consists of n variables and m clauses. We are also given a pair of its satisfying assignments, alpha s and alpha e. We will then create an instance of EK sat reconfiguration as follows. The formula is denoted by psi. We first create new k-3 variables, y1 through yk-3. For each clause Cj, we append a possible clause over yi. Since there are 2 to the k-3 possible clauses over yi, we obtain m times 2 to the k-3 clauses. And the two satisfying assignments for the formula psi are defined as shown in the slide. It is easy to see that the perfect completeness is preserved by this reduction. And in the soundness case, if the optimal value of the first problem is less than 1 minus epsilon, then the optimal value of the second problem is less than 1 minus epsilon over 2 to the k minus 3. So we obtain that 1 minus omega 2 to the minus k factor approximation is p-space hard. And this factor is optimal for max EK sat asymptotically. In the second attempt, we will improve the inapproximability factor to 1 minus omega 1.92 to the minus k. We will describe a gap-preserving reduction in the language of PCP verifiers. We start from gap E3 sat reconfiguration problem with a constant gap epsilon between the completeness and the soundness. In the step 1, we will construct a 3 lambda query Horn verifier. The gap between completeness and soundness becomes omega epsilon over k. In the step 2, we will emulate the Horn verifier by using an OR predicate verifier, which can be described by KCNF formula. And the gap becomes omega epsilon over 1.92 to the k. For each verifier, we would like to find a path that maximizes the minimum acceptance probability of the verifier. And let opt denote the optimal value of the verifier. In the first step, we will construct a 3 lambda query Horn verifier for gap E3 sat reconfiguration. As an input, we are given a 3CNF formula phi over m clauses, and we are also given an oracle access to assignment alpha. We first sample I1 through I lambda from the integers from I to m uniformly at random. Then we will check if the Horn-like condition shown in the slide is satisfied by the assignment by making oracle access to the assignment alpha. If the condition is satisfied, then we accept. Otherwise, we reject. Then it is easy to see that the perfect completeness is preserved by this verifier. And in the soundness case, if the optimal value of maximum E3 sat reconfiguration is less than 1 minus epsilon, then we can show that the optimal value of this Horn verifier is less than 1 minus order of epsilon over lambda. We will explain why this relation is true. I will explain that the Horn verifier is non-monotone. Suppose that the fraction of the clauses violated by the assignment alpha is equal to epsilon. Then, the rejection probability of the Horn verifier is equal to epsilon times 1 minus epsilon to the lambda minus 1. This can be observed from the negation of the Horn-like condition. And this figure shows the rejection probability of the Horn verifier with respect to epsilon. You can see that it is maximized when epsilon is equal to 1 over lambda. And if epsilon is close to 1, then the rejection probability is close to 0. In this sense, the Horn verifier is useless in the standard PCP regime. But in the reconfiguration world, the Horn verifier is useful. The key observation is that any path from alpha S to alpha E contains some assignment alpha circle such that the fraction of violated clauses is approximately epsilon over lambda. So, we can show that the rejection probability of the Horn verifier is approximately equal to omega epsilon over lambda. This implies the soundness property, and this explains why the monotonicity of the verifier can be useful. In the step 2, we will emulate the Horn verifier by using an OR predicate verifier. Recall that the rejection condition of the Horn verifier is like this. It is easy to see that the number of rejecting local views of the Horn verifier is 7 to the lambda minus 1. Therefore, we can emulate the Horn verifier by using an OR predicate verifier so that the rejection probability of the OR verifier is equal to the rejection probability of the Horn verifier times 1 over 7 to the lambda minus 1. By this relation, it is easy to see that the perfect completeness is preserved. And in the soundness case, if the optimal value of the Horn verifier is less than 1 minus omega epsilon over lambda, then the optimal value of the OR verifier is less than 1 minus omega epsilon over 1.92 to the k. This completes the proof of the p-space hardness. In this video, we demonstrated that the approximation threshold for max-min EK-SAT reconfiguration is 1 minus order of 1 over k. Immediate open questions are to find more applications of non-monotone verifiers and to find a class of Boolean relations for which max-min satisfiability reconfiguration is harder to approximate compared to max-SAT. Thank you for listening.